NASA, the most storied space agency in history, a titan of celestial exploration forged in the fires of the Cold War, approaches SpaceX with an incredible offer. It's a state-of-the-art, multi-million-dollar docking system, the product of over a decade of painstaking work by the world's most brilliant aerospace engineers. This system, known as the NASA Docking System or NDS, was a masterpiece of intricate engineering, meticulously designed for what is arguably the most dangerous and delicate maneuver in all of spaceflight, linking two vehicles together in the unforgiving void. And this technological jewel was being offered to SpaceX, the brash newcomer, completely for free. So why did SpaceX look at this gift horse, this pinnacle of traditional engineering, politely say no, thanks, and decide to build their own system from scratch, allegedly finding their inspiration not in an advanced lab, but in the rugged mechanics of a mountain bike? The answer to that question is not just a technical footnote in aerospace history. It reveals the very core of the philosophy that is allowing SpaceX to completely upend a multi-billion-dollar industry. It's a profound lesson in how to solve problems that seem impossible. A lesson that goes far beyond rockets and spacecraft. This isn't just a story about metal, circuits, and orbital mechanics. It's a story about two completely different ways of thinking, a clash between the cathedral of tradition and the garage of revolution that would ultimately redefine the rules of engineering for the 21st century. To truly grasp the audacity of SpaceX's decision, you have to understand the sheer magnitude of what they were turning down. The task of docking two objects screaming through the vacuum of space at over 17,000 miles per hour is about as high stakes as it gets. These are not gentle maneuvers. They are, at their heart, controlled collisions where the slightest error, a tiny misalignment of millimeters, a fraction too much force, a single line of faulty code, can spiral into an unmitigated catastrophe, endangering the lives of the astronauts and the integrity of the $100 billion International Space Station. A failure here could mean a puncture, a debilitating spin, or worse. For decades, the history of spaceflight was a slow, cautious climb up a ladder of increasing complexity. The earliest systems, like the probe and drogue mechanism used in the Gemini and Apollo programs, were relatively simple but mechanically aggressive. An astronaut would manually fly a probe on their capsule into a cone-shaped receptacle on the target vehicle, a nerve-wracking process that relied entirely on pilot's skill. A major evolutionary step came with the historic Apollo-Soyuz mission, which demanded a universal, androgynous system that either side could dock with. This gave birth to the APAS, or Androgynous Peripheral Attach System, a more sophisticated design that later evolved into the APAS 95s, the very system that connected the American space shuttle to the Russian Mir space station. Each iteration was guided by one principle: extreme caution. This philosophy culminated in what was supposed to be the universal key for docking in the modern era, the NASA Docking System, or NDS. Evolving from an earlier design called LIDS, Low Impact Docking System, the NDS was an engineering marvel, built to achieve a zero-impact connection Think of it like a surgeon performing microsurgery in zero gravity. The system was active, meaning it used a complex thinking dance of sensors, 6 servo-actuated electromechanical legs, powerful electromagnets, multiple motors, and layers of sophisticated software to gently sense and pull 2 spacecraft together. It was designed to think, feel, and react, making the final connection as soft as a whisper to avoid placing any stress on the aging structure of the International Space Station. This was the absolute pinnacle of old space engineering. It was built on layers upon layers of electronic and mechanical redundancy, operating under the assumption that complexity was the only true path to guaranteeing reliability. The NDS was heavy, it was expensive to develop, and it was incredibly hungry for electrical power. But it was also the flight-ready product of the most experienced space agency on the planet. When NASA awarded SpaceX the multi-billion-dollar contract to fly its astronauts, it required them to use an internationally compatible system based on the International Docking System Standard, IDSS. Offering them the completed NDS design seemed like the most logical, safest, and most efficient step forward. Any traditional aerospace company would have leaped at the chance to integrate this NASA-blessed technology. But SpaceX's thinking was anything but traditional. To the complete and utter bewilderment of NASA's old guard, SpaceX politely declined to use the existing NDS design. This wasn't arrogance or a case of not invented here syndrome. It was a direct, unfiltered application of their core philosophy, one that comes straight from the mind of Elon Musk and his almost dogmatic method for solving problems, reasoning from first principles. First principles thinking, a concept that dates back to the philosopher Aristotle, means you don't start by looking at what's already been done. You don't just try to improve on existing solutions by analogy. A process Musk argues only leads to slight variations and incremental, predictable improvements. Instead, you break a problem down to its most fundamental, undeniable truths. The things you know are absolutely true based on the laws of physics, and you build your solution up from there. It's the essential difference between asking, how can we make a slightly better, lighter, or cheaper version of the NDS? And asking, what is physically required to join 2 objects in orbit and create a safe passage between them? One path leads to refinement, the other, potentially, to revolution. So instead of accepting the deeply ingrained premise that docking had to be a delicate, sensor-driven, zero-impact maneuver, SpaceX engineers stood before a whiteboard and asked a totally different set of questions. What is the real goal here? To securely join 2 spacecraft, absorb any residual motion, and create a pressurized seal for crew and cargo to pass through. What are the fundamental physical challenges? Managing the kinetic energy of the impact and correcting for any misalignment in the final approach. What is the absolute simplest, most robust, and most mechanically reliable way to solve for that energy and alignment problem? This is the heretic's question that challenges decades of institutional tradition. It's the question that implies that the complex, painstakingly developed, multi-million-dollar solution might not actually be the best one. It forces you to confront the possibility that the fortress of complexity, built to ensure safety, might have inadvertently become a prison, trapping engineers in a cycle of iterative improvement when a complete breakout was possible. And the answer they eventually found wasn't in more complex software, more sensitive sensors, or more advanced actuators. Famously, the initial spark of inspiration was found in a bike shop. A legend, which has since been confirmed as fact, goes that a couple of SpaceX engineers, instead of sourcing expensive, custom-designed aerospace parts, went to an online cycling shop and bought off-the-shelf mountain bike shocks. Their initial prototype was so rudimentary, built with these shocks and other parts from an industrial supply catalog, that it quickly earned the nickname the McDocker. The core inspiration wasn't the delicate thinking system from NASA, but the rugged, brute force simplicity of a bike's suspension. A mountain bike doesn't try to avoid bumps with a complex network of sensors and motors. It's designed to hit them head-on and use simple, robust mechanical parts, springs and dampers, to absorb and dissipate the energy. This beautifully simple concept became the very heart of the SpaceX docking system. Instead of a zero-impact system, they engineered a mechanically elegant, energy-absorbing one. I thank you for watching. I'm Prime Corey. I'm fascinated. Internal. Their docking mechanism doesn't have a complex brain of active controls running sophisticated software. It has simple, passive latches and mechanically actuated components that work with physics, not against it. When the Dragon capsule approaches the ISS, it doesn't aim for a perfect force-free kiss. It makes contact, and the mechanical system does all the work. The system is brilliantly designed to absorb the force of the impact and use that very energy to guide the docking ports into a secure, hard, locked position. It handles errors and misalignments, not through a complex, reactive software algorithm that could glitch or fail, but through sheer physical toughness and an incredibly clever mechanical design. The difference in philosophy is stark. Where NASA's NDS used active software and 6 power-hungry electromechanical arms to cushion the blow, SpaceX used simple springs and dampers. Where the NDS had a complex web of electronics, sensors, and motors that all had to work in perfect concert, SpaceX had passive latches that snapped shut mechanically. Though both systems ultimately meet the same international standard, SpaceX's first principles approach resulted in a mechanism that was dramatically lighter, far less complex, used significantly less electrical power, and was orders of magnitude cheaper and faster to design, build, and test. It was a direct, physical challenge to the long-held aerospace belief that complexity equals safety. SpaceX made a bold bet that in the harsh, unforgiving environment of space, real reliability comes not from adding more layers of redundancy, but from having fewer things that can break in the first place. NASA's initial reaction was, to put it mildly, profound skepticism. When SpaceX engineers first presented their elegantly simple design, they were met with blank stares. To many at the agency, who had spent their careers perfecting the art of the gentle, zero-impact connection, The McDocker concept seemed like a reckless and naive oversimplification. The idea of intentionally bumping the multi-billion-dollar space station was deeply unsettling, and the novel design was even cited as a potential weakness in SpaceX's competitive bid to fly NASA's own astronauts. The pressure was enormous. The entire multi-billion-dollar commercial crew contract could be at risk if they couldn't convince NASA that their radical new idea was not just viable, but fundamentally safe. But SpaceX didn't back down. Instead of arguing, they followed another one of their core rules. Test, test, and test again. The McDocker prototype and its descendants went through a grueling and exhaustive campaign of over 450 soft capture tests on the ground. These tests, some conducted in close collaboration with NASA, simulated every conceivable scenario. Different approach speeds, various angles of attack, and numerous off-nominal conditions, proving again and again that the simple mechanical system was more than robust enough to handle the job. Slowly but surely, the culture at NASA began to shift. Agency engineers who visited SpaceX's facilities to see the hardware for themselves walked away impressed by its robust simplicity. The deep-seated skepticism gradually transformed into cautious, data-driven optimism. The ultimate moment of truth came on March 2nd, 2019. The world watched, holding its breath, as the uncrewed Dragon capsule on its pivotal Demo 1 mission flawlessly approached and docked with the International Space Station. It was the first time a private company's spacecraft had ever achieved this critical milestone, and it did so with a system born from first principles and inspired by mountain bike parts. Since that day, the SpaceX docking system has become a reliable workhorse for the ISS, proving its precision and robust reliability time and again with dozens of missions. It has successfully carried astronauts on long-duration crew rotations like Crew 6, Crew 8, and Crew 11, and delivered vital cargo on numerous flights, including CRS-29 and beyond. A long succession of textbook dockings broadcast live around the world were the final, irrefutable vindication. SpaceX hadn't just built a cheaper or simpler system. They had arguably built a better one. This story is a perfect example of the innovation process SpaceX applies to everything they build. It's the same first principles thinking that's enabling them to land and reuse orbital rockets and to develop the world-changing Starship. So what other established technologies in our world do you think are long overdue for a complete reinvention from the ground up? Let me know your thoughts in the comments below. This decision to ditch a free, flight-proven technology wasn't just about a docking port. It was a declaration of a new philosophy for the 21st century space race. As SpaceX Vice President Kiko Donchev famously says, "Complexity is the devil." That idea is now embedded so deeply in the company's DNA that it functions like an algorithm. Elon Musk has since articulated the SpaceX design process into a simple, 5-step algorithm that they strive to apply with religious rigor. First, make the requirements less dumb. Requirements often come from people, not the laws of physics, and are therefore fallible. They should always be questioned, especially if they came from a smart person, as you might be less inclined to challenge them. Second, and most importantly, try very hard to delete the part or process step. Musk insists that if you aren't finding yourself adding parts back into the design at least 10% of the time, you are not deleting aggressively enough. The bias is always to add just-in-case parts, and this must be fought. Third, simplify and optimize the design. Only after you've questioned the requirements and deleted every possible part do you work on making what's left more efficient. Only then, as the fourth step, do you accelerate the production cycle time. The final, fifth step is to automate. Most companies get this order completely reversed, trying to automate and accelerate a process that is fundamentally too complex and has unnecessary parts, which Musk describes as a direct recipe for failure. You can see this algorithm in action everywhere at SpaceX. They didn't just accept that rocket fairings, the multi-million-dollar nose cones, were disposable. They questioned why, leading to their successful recovery and reuse with giant nets on ships. They didn't accept the exorbitant price of aerospace components. They broke them down to their raw material costs and realized they could build them in-house for a tiny fraction of the price. This exact same thinking is now being applied at a monumental scale to their most ambitious project, Starship, the program aiming to make humanity a multi-planetary species. In fact, the docking system being developed for the lunar Starship lander is a direct evolution of the flight-proven, mechanically simple design from Dragon, adapted for a new generation of deep space exploration. The rejection of NASA's complex design was a pivotal turning point. It proved that in the world of high-stakes, life-or-death engineering, elegance and robustness are often found in simplicity. It showed that by breaking a problem down to its physical core, a small, agile team could innovate far beyond a decades-long, resource-heavy institutional effort. This wasn't about disrespecting NASA's incredible legacy of achievement. It was about forging a new, faster, cheaper, and more efficient path forward. This is the philosophy that isn't just building more reliable docking ports. It's the philosophy that's building the future of space exploration, one fundamental truth at a time.